What is this? All right, that's a battery. If I were to list some of the top innovations in like scientific history, hopefully you guys would agree with me. I think a battery actually has to be on like anyone's top 10 list. I mean, I think there's a lot of really amazing things we've done in science, from like the discovery of the electromagnetic induction effect, if you guys have done physics, to vaccines and biology. But like the ability to have power, electricity stored temporarily in a battery, hasn't it fundamentally changed our world? Right? I mean, this is something that has really become very advantageous even in the last 10 years. Okay. What's probably the single most important device that now runs on a battery that we didn't have 10 years ago, that everyone in this classroom has? Your cell phone, right? Cell phones actually existed, by the way, like 20 years ago. Anybody ever seen those big brick ones that were like this big here? That like, this dates me, but if you ever watched the television show Saved by the Bell, this is really old. You've seen it though? You know, he used to have the big honking brick cell phone, and that was in the 90s. But the problem with those is that they didn't really have a good power supply. Now, a decent battery on a cell phone depends on how much you're on Snapchat during the day, but like it can last you for 8 to 12 hours, right? My phone more or less lasts me all day. And who has to recharge their phone during the day? Okay. So, but for the most of the rest of you, your phone can last you basically an entire day. Isn't that incredible though, that we have the ability to have portable power, for lack of a better word, that we can just take with us. Oh, and so to me, this is one of the most interesting units because that's what we're going to talk about. We're going to talk about electrochemistry. Basically, the idea of how can we fit well, what is electro referring to? Movement of electrons, yeah, right? We're going to talk about the movement of electrons, which isn't movement of electrons just a fancy word for electricity? Why don't we start with that? Do you guys know what electricity is? Movement of electrons, right? When electrons flow through a closed circuit, we have electricity. Now, we can do that from a lot of other different sources. Like we can use a generator or a motor and use things like that to make electricity. But really, the main focal point of this unit is to talk about how we can use chemicals to make batteries. Right? And so there are batteries in your cell phone, but there's also batteries in your calculator, right? You guys know what a double A or triple A battery is, right? Right, we're going to talk in this unit about primary and secondary batteries. Why don't I pause for a second here? Anyone want to hazard a guess as to the difference between a primary and a secondary battery? I'll give you a hint. Your calculator has a primary battery, and your cell phone has a secondary one. What's the difference? Yeah, one can be recharged. Yeah. So we're going to talk about how things can be recharged, how that works. We're going to talk about how much voltage and how much current batteries can provide, and how that's useful when it comes to whatever device you want to run. But overall, our main purpose, though, is to talk about the chemistry behind this. Because, hey guys, it's not like some sort of magic that obviously causes electrons to move. We have to talk about what exactly causes electrons to start flowing through a circuit. You know, what mechanism causes them to actually move. So, does that kind of make sense as our preamble? That's where we're going this unit. Okay. So, my first two lessons are very much fundamental concepts. I'm going to talk today about a lot of vocabulary. It's kind of a boring lesson in a way because we're not going to do a whole lot yet. We're getting there. But I have to make sure we're all talking about the same terminology. Okay. For example, has anybody ever heard of anodes and cathodes on a battery? They're the positive and negative sides of a battery, right? And so you can just refer to it as the positive side or the negative side. But instead, we'll talk about them as anodes and cathodes instead. So today is a lot of vocab. Fair enough? Why don't we start working through the stuff I put down here? The main concept we need to talk about in our unit here is a new type of reaction. Okay, we have learned many chemical reactions so far in your chemistry careers, I guess. Let's give a list here real quick. You should know single replacement, double replacement, formation, decomposition, combustion, cellular respiration, photosynthesis. I already mentioned combustion, so that one kind of already takes place. You should know ionization and dissociation, right? Well, we're going to add a new type of reaction to the list here. This is known as a redox reaction. And redox is actually a melding or merging of two words. The words are reduction and oxidation. You guys can see those sitting right there. Hence the name redox, reduction, oxidation. It's actually two parts. And I want to use an analogy to begin to maybe help understand the concept here. Reduction oxidation reactions are going to involve electrons. That's really our focus this unit. Electrons that move somehow. Okay. Now, there's always two parts to this. There's always someone who gives away electrons, and there's always somebody who receives electrons. And I'm going to use an analogy of money, for example. Imagine that you have just a basic exchange where I pay Daniel for something. Right? So I pay him $10 because he did my homework for me. No, that's a bad example. I paid him $10 because he sold me a Xbox controller. I don't know. Right? From the perspective of the electrons, in this analogy, the electrons will be the money that I transfer, right? Someone is going to give money away. Someone's going to give the electrons away. And someone is going to be the recipient of the electrons. Does that make sense? And that's why there's two halves to this. Eventually, I'll get to these words a bit more in detail, but that's the concept I've got right here. It's even my second bullet here, right? When one substance loses electrons, why is this not working? Come on. There we go. When one substance loses electrons, the other one gains electrons. And so just like with so many things in chemistry, we have a law. Okay? You guys have learned some of these laws before. There's laws of conservation of mass. There's laws of conservation of energy. For those of you guys who have done physics or those who are about to do physics, what I'm basically describing is this. I'll even write it down. This is the law of conservation. Oh, I heard someone say it. Of charge, yeah. And this is something that we'll do in physics a bit more, but that's essentially what this bullet right here says. Okay? This has to be logical, does it not? If I am going to give Daniel $10, Daniel has to receive $10. If copper is going to give away 2 electrons, something else has to receive 2 electrons. They can't just magically vanish. Does that concept make sense? And so it's very fundamental, but it needs to be said. There's a law of conservation of charge. As electrons eventually go through a loop, imagine you have just a basic circuit here. You have a battery. Here's a battery. And you hook some wires up to it, and you hook some wires up to it, and it goes to your clock. 12, 1, 2, 3, 4. You guys get the idea, right? The electrons go through the circuit and around through the circuit. That's effectively what electricity does. Right? When does the battery stop running? More or less, yeah. As soon as all the electrons have gone around, then the battery stops. There are other reasons, by the way, it could stop as well, but that's a good reason as any. When does your cell phone die? Well, when all of the electrons have run through the circuit and gone to the other side, it stops. But you know what happens when you recharge your cell phone? Yeah, recharging the cell phones sends the electrons back to start. Hence the idea between a primary and secondary cell. Can you recharge it or not? Does this make sense so far? I'm getting a little off topic. But what I need for you guys to know then is that redox reactions are happening everywhere. What we're going to do is we're going to classify some reactions as redox, but they might also be single replacement or double replacement. It might fit more than one category. As long as I can find you a reaction where I can show you that electrons are moving, it's known as redox. Okay? If you have someone who's gaining electrons and someone who's losing electrons, or someone who's giving money and someone who is taking money, right? That's what we're talking about in terms of vocabulary. Now, before I get to those definitions a bit better, I want to go back to a little bit of a history lesson here. I don't necessarily know that I'd call them chemists, but mankind has actually been working with reduction and oxidation reactions for centuries, millennia. We didn't necessarily know the nitty-gritty about what was happening, but they've been doing these reactions for a long time. In terms of some of the most important historical achievements, the turn of the 20th century, about 1905, 1907 or so, is really when some of the big chemistry breakthroughs came through. Does anybody know what I'm hinting at here? What happened in the early 1900s? Rutherford. What did Rutherford discover? Rutherford discovered the nucleus, right? And by knowing about the nucleus and knowing where electrons are at, now we start to know a little bit more about the structure of matter. But if you're talking like 300, 400, 500 years ago, we're talking like John Dalton's model of the atom. Do you guys remember John Dalton's model? It basically was like a billiard ball model where hydrogen is this ball here and carbon is this ball here, and it was a very primitive model. It was okay, but it wasn't nearly as complex as we know now. Now we know about subatomic particles. We know about our protons, our neutrons, and our electrons. But it really wasn't until about the Ernest Rutherford time when we started to realize truly how electrons and protons and neutrons worked. So what I want to do on these slides right here is I want to talk about thousands of years ago, well before we had any chemistry knowledge of what's happening. And I want to show you some knowledge of actually of reduction and oxidation type reactions. The word I want to use here, I think I'm saying it right, is metallurgy. And basically the idea here is it's science and technology kind of put together, but very specifically for metals, hence the name metallurgy, right? We're all about metals in this branch here. Imagine that it's 3,000 years ago, 4,000 years ago. I don't know, pick an old time frame here, okay? And you need to farm. Okay? Now, you got a couple options here. You could try to plow your field with an oxen, and behind the oxen, you are trying to, turn up your field, and you need something to do that. You know what you might use? A rock. Okay? But that's pretty primitive, right? Eventually, we discover, hey, what if I could make some sort of like tool, a spade of some type? Well, a rock might work, but it's really hard to shape rock because it cracks into pieces, right? Well, eventually we discover, hey, let's use some sort of metal, right? And maybe you guys have had me tell you this story before, but like we're talking about going into things like, say, the Bronze Age, where all of a sudden we realize, hey, rather than using these metals here, what if we melt a couple different ones together? And all of a sudden we make this really, really stronger metal. And I mean, really, when it comes to things like bronze or steel's another really good example here. Those usually are an advent not only in technology, but also in war, by the way. Like, have I talked with you guys about this idea before? Is that if you're the guy over here that's trying to fight with a stick, and this guy over here has a sword made out of steel, who wins that fight? Well, the guy with the steel sword, right? But that's the time frame I want you guys to imagine here, okay? And I wouldn't call them scientists, but the idea of trying to extract metal, I mean, even to this day is very important. And so that's what I want to talk about here is the idea of trying to extract naturally occurring compounds to make use of them. This actually even matters in 2018. I brought up steel. Anybody know why steel's really big in the news right now? Because Donald Trump is you guys know this already. I don't need to tell you this. Yeah, he's trying to put tariffs, if you guys know the social studies aspect of this, on steel across the border. But like even today, the extraction and procurement and refining of metals is super important because literally we build our stuff out of metal. So I want to go to my next slides here finally. But here's the basic concept here. As we go through history for thousands of years, I mean, right here, we've got people, they made their stuff out of just basic copper. What's the downside to copper? Copper will, yeah, it'll break, it'll rust. Same thing with iron. It has that ability to break and rust and decompose. But hey, bronze is a little bit stronger. Eventually you make brass. Well, again, I don't want to call them scientists, but as people discovered more and more metals and realized, hey, I can make a shovel out of this. Hey, I can make a bullet out of this. Hey, I can make a sword out of this. Technology advanced. Does that make sense? And so I've got these examples here. Copper, and then bronze, and then iron, zinc, and aluminum were discovered, but it's really from heating ores of metals. Okay. So I need to pause for a second. Do you guys know what the word ore means? Not a paddle ore, but like a chemistry ore. Do you guys know that word? No one's nodding their heads, so let me show you. I've got a slide on it. This right here, and this right here, those are all example of ores. Okay. They are mixture compounds. I shouldn't say mixtures, but they're compounds that have the element that you want in them. For example, this is an ore of iron. This is an ore of tin. This is an ore of copper. Okay. I want to give you an example of one that's actually really common. You guys probably have seen this formula before. It's Al2O3. What do we call that? Aluminum oxide. I'm going to try Google it today. Hey, Google. What's another name for aluminum oxide?
On the website dictionary.com, they say, alumina occurs naturally as the mineral corundum and, with minor traces of chromium and cobalt, as the minerals ruby and sapphire, respectively. In its
That's not what
hydrated
I
form,
asked.
it also occurs as the rock bauxite,
There it is.
also called aluminum oxide.
Here we go.
Chemical formula, aluminium oxide.
Okay, did you catch that last part there? That's actually what I wanted. It's called bauxite, Bauxite. I'll write this out. Bauxite. If you were in a mine, okay, I grew up in British Columbia, in the southeast corner. There's a lot of mines by Sparwood and Kimberley. Anybody ever traveled around there? There's a lot of mines down there where they're trying to find metals. Well, if you wanted aluminum, you don't just find pure aluminum lying around. You find ores of aluminum. You find ores of silver and gold and copper and stuff like that. And so if you were to be in an aluminum mine, this is what you'd find. It's called bauxite. Here's the issue, though. Is this pure aluminum? No. So I want to go back a slide here. Early chemists, scientists, people who were working with metals, the metallurgy people, they gave a name to this. They called this reduction. Reduction basically meant turning something into a pure metal from a compound. Basically, the word they used, like the verb they used, is they would reduce something. And you can probably actually see why we would call it reduction. This thing right here, bauxite, aluminum oxide, is it pure aluminum? What do we not want? We don't want the oxygens. Does that make sense? So if you can find a process with which to turn this into aluminum and some oxygen, we called this reduction because we were reducing the formula so that this part was no longer there. Does that make sense? Now, they had no idea what they were doing from a chemistry point of view. They knew nothing about protons, neutrons, electrons, all of that subatomic stuff. But they did know, hey, here's this rock. I'm going to heat this rock up. Hey, look, it melted. Hey, look, it's now stronger than it was before. Because you know what happened? When they heated it up, it decomposed. And by decomposing, it turned it into pure aluminum. Oxygen, the oxygen gas bubbled off. You let it cool, and all of a sudden you got yourself some pure aluminum. You let it cool inside of a mold, and all of a sudden now you've got yourself an aluminum sword. You probably wouldn't make a sword out of aluminum, but you get what I'm saying here? Okay. So historically, that's where this came from. Reduction means producing metals from their compounds. And so I've got a few different examples here. This is just a basic iron oxide compound, but you add it to some carbon monoxide, and all of a sudden you make yourself some pure iron. Sweet. Now that I have some pure iron, I can make something with it. A shovel, a bullet, I don't know, pick whatever it is, right? Here's some tin oxide. Add it to some carbon, and all of a sudden we've got some pure tin, or some copper. Add it to hydrogen gas, it makes ourselves some solid copper. The real key to this reaction is that these things turn into that one right there. A compound turned into an element. Purifying it, and the word reduction hence came to be. Does that make sense? Now look at these reactions. These are actually reduction reactions. But wouldn't you argue that we could also classify these in other ways? For example, this last one right here. Could we not classify this last one as single replacement? Do you guys see that? So I need you guys to know that reactions don't necessarily fit into one category or another. Sometimes they can fit into multiple categories. It can be a single replacement reaction that is also reduction. You get what I'm saying? So this is my last point here. I've already mentioned this, but humans were reducing metals far before they understood the chemistry involved, right? We're talking actually knowing about chemistry for maybe 250 years. And even that is probably generous. We're probably talking really knowing what we're doing for about, I would say 120 years, give or take. But people have been working with metals for thousands of years. So that's reduction. Now, there was an opposite to reduction as well. And we actually have a different name for this. We've now given it the name corrosion. And you guys have heard this word before, right? Corrosion means to rust something. But its name thousands of years ago was known as oxidation. And it's kind of the opposite process, where what you have is a pure metal. You expose it to an element, usually oxygen, and it turns into a rust of some kind. And you guys are probably all familiar with the rusting process to some degree, right? You leave your piece of metal outside in the rain and the elements, and over time, eventually the outer surface gets coated with some sort of rust. Well, isn't that the opposite process? A pure metal getting turned into a compound, right? And all metals rust. Aluminum, copper, silver, gold, like all of them have some sort of compound they can form into. Hey, you guys want breakfast? I see muffins, yogurts, bananas, apples, oranges, cheese. Where's Joselle? She'd be on this. Well, I know, but she was here, like, to start class. Oh, okay. Surprised she doesn't come back here again to get double up. All right, thanks so much. Okay, now I've got some examples here of oxidation reactions. Now, when you look at these, I can also classify them in another way. Although we're going to call them oxidation, you probably could also argue that these are all formation reactions, right? Because what we're doing here is we're taking two different compounds and we are forming one thing from them. Right? Now I got to point one thing out though. Historically, they called it oxidation because many things you can add oxygen to and make a compound out of. But that's really limiting. So even though we still call it oxidation, all of these are actually examples of oxidation. The first one actually involves oxygen. But see how this one doesn't involve oxygen? But at its core, is it still not doing what we want? We are taking a pure metal and we are turning it into a compound. And here we are taking a pure metal and we are turning it into a compound. That's the definition. So I want to make sure I'm clear. Oxidation does not actually mean you have to add oxygen to it. But historically, we called it oxidation because many things, when you add it to oxygen and water, will rust. Does that make sense? So, reduction, compound, refine it into pure metal. Use that metal to make a sword. Opposite of that, oxidation. Take that metal and turn it back into a compound. Right? They're kind of opposites of each other. But like I said here, do oxidation things actually have to involve oxygen? No. Now, I realize as I look at my slide here, I've skipped an important word I should talk about because this is mostly terminology today. So let me go to this one right here. The word is called an oxidizing agent. Okay. So let's say we're all on the same page, I hope here. Oxidation then means we're going to take something and we are going to turn it from a metal into an ore of some kind. Anyone want to guess what an oxidizing agent is then? Well, not a catalyst, so to speak. A catalyst, it itself is not part of the reaction. Right? We write the catalyst on top of the arrow because it does not get consumed. But like if this thing has to turn into this thing right here, who is the oxidizing agent? These guys here. Does that make sense? Like, hopefully the terminology is just even intuitive. If you have an agent of something, it is the thing that causes something else to happen. So if the magnesium is going to turn into magnesium oxide, it doesn't do that without an oxidizing agent making it happen. And so that's the guys in the middle column here. This guy here is an oxidizing agent. This guy's an oxidizing agent. This guy's an oxidizing agent. Even though they are not actually oxygen, you don't have to be an oxygen to be an oxidizing agent. Okay. Well, that same logic occurs if you want to go back to my reduction slides. I think I skipped this. Here, let me erase this. We'll look at what I skipped here. Okay, who's getting reduced? Hopefully you'll agree that this thing right here is a compound, and it is being reduced into iron. That makes sense? So then who is the reducing agent? Well, the reducing agent is everything in this column right here, because those are the things that cause something else to get reduced. So let's talk terminology. We're going to use people here, I guess. Max and Sam, we're going to use you guys today. Sam, you're a compound. And we're going to try to turn you into a metal. And in order to do that, Max is going to change you into a metal. Okay, so here's how I would describe this. Since Sam is getting turned into a metal, we would say Sam is being reduced. But since Max is going to cause him to change, we would call Max the reducing agent. Does that make sense? So whoever is getting reduced, the other item is the agent of reduction. I don't know if that helped at all, or that was just silly, but it was fun. Okay, now I want to fast forward now thousands of years. It wasn't until J.J. Thomson discovered the electron with his cathode ray tubes that we actually even knew about subatomic particles. And I don't even know that Thomson fully understood what he was getting into. So, I mean, again, we're talking like 150 something years ago, basically, and all of a sudden we now know about electrons. Now, all of what I told you is still valid. Like, metals still get reduced, and compounds get reduced and metals still get oxidized. But all of a sudden, once we know about electrons, we were able to delve a little bit deeper into this process because there was actually electron transfer taking place, and we had no idea. But of course, they had no idea. They didn't have microscopes. They didn't have the tools to even recognize electrons because aren't electrons basically about as small as we can basically have something? Right? If you've taken my physics class, you'll know that there's actually stuff smaller than electrons. Spoiler alert for you guys next year. There is actually stuff smaller than electrons, but more or less electrons are about as small as it gets. Okay. What we've discovered though is that when these processes were taking place, when a metal was turning into an ore, or when an ore was turning into a metal, there was actually an electron transfer taking place. And so we've got some new definitions we use to describe them, and this is like the classic mnemonic device. You guys know what that is, a mnemonic device? A mnemonic device is like where you make like a silly little saying, so you can like memorize things based on the first letters of the words. So this is what I learned back in my high school. I'm going to teach it to you still. So the acronym or the mnemonic is called Leo says GER. Okay, and it helps you remember which one is which. Leo is loss of electrons. We now know
because of our knowledge of electrons that anytime things are being oxidized, they're actually losing electrons.
And grr, because Leo the lions say grr, right? Anything that is being reduced is actually gaining electrons. And I want to go back a few slides here, and I want to show you how I know that to be true. Because now that we know about charges on ions and atoms, I can actually visually show you this. So go back in your slides. Let's go to, say, this one here first. Lav is even doing this literally right now with his grade 10s. Okay, because I was watching him do this on the board. You guys would have learned this at some point. How do I know how to make this Fe2O3? Well, at some point in your lives, you probably learned that iron has a +3 charge and oxygen has a -2 charge, and you kind of learned how to piece that together. Does that make sense? What would the charge on an iron be, though, if it's by itself? Is it an ion? Or is it an, what's the other word we'd use? If it's not an ion, it's an atom. And the charge on an atom should be neutral. Now, I want you to consider the changes here. Hopefully you guys are all in agreement. This is an ion because the iron is combined with another ion forming an ionic bond, right? And right here, iron has a +3 charge. But right here, iron has a 0 charge. Now, how in the world can a +3 turn into a 0? Well, you could do one of two things. If you're going to go from +3 down to 0, you could lose some positives. If you want to go from +3 down to 0, you could lose positives. Is that how chemistry works, though? Well, no. We now know that the electrons orbit, so more or less, and that the protons are tied to the nucleus. So if you can't lose your protons, what's the other option? You can gain electrons. And so we can actually visibly see that right here, this iron right here must have gained 3 electrons. For it to go from a +3 ion, cation, to being a neutral atom from a +3 to a 0, it must have gained 3 electrons. Right? Well, there's a pattern here. Let's keep looking. I'll do the last one here. At some point, you guys would have learned about how to name this compound. This is copper 2 sulfide. And I know it because sulfur is -2 and copper is +2. Well, right here, copper is an atom. It must have a charge of nothing, right? It's neutrally charged. But this guy right here, by virtue of it being an ionic compound, this is a cation, this is an anion, it has a +2 charge. How do you go from +2 to 0? Well, again, 2 ways, right? You either lose your protons, but that's not actually possible, or you must gain 2 electrons. Does that make sense? Well, here's where someone really clever came along. Once they started realizing, hey, as chemical reactions are taking place, electrons are moving. And they also realized, hang on, isn't the movement of electrons also known as electricity? Let me say that one more time. Someone comes along and realizes electron movement is taking place. Can't I visually show it here? That in order for these charges, these ions to have changed, electrons must have moved. Don't we already know that anyways? What are bonds made out of? Electrons. Secondly, doesn't the movement of electrons create electricity? So someone really clever said, what if we could try to find a way so that when this molecule here and this molecule here, when they react, there's going to be an electron going from left hand to right hand. Does that make sense? Somewhere in there, an electron's moving around. They suggested, what if I could find a way to make that electron go from here to here, but rather than going directly, what if I ran it through a wire in a loop all the way around the long way, and then I could create myself a circuit? Does that make sense what I'm getting at? Let me try to diagram this. Here's compound A, here's compound B. Here's A and B. If we now all agree that somehow an electron is going to move, as these two things come together, and eventually A touches B, if an electron is going to move, that's fantastic, awesome, great, something new got made. But someone was really brilliant and said, what if I put a barrier in the way? And I make it so that the electron cannot physically go from A to B. And instead, the electron goes the long way around. So the electron goes to there. What have I now made? A circuit. And this is literally how a battery works. I'm going to show you this more over time, but effectively, this is now the negative side of your battery, and we call that an anode. And this is the positive side of your battery, and we call that a cathode. And hence the advent of batteries. And for the last 150 or so years, hey Google, when was the first battery made?
1800. On the website science.howstuffworks.com, they say, in 1800, Volta created the first modern-day battery when he built what came to be known as his voltaic pile.
Okay, so 218 years, right? As we've been discovering this, we've now gotten to the point where a battery is so small that it can literally fit inside your cell phones and be recharged, or can be so small you can actually put it inside a pacemaker, inside of like someone's heart. That's how tiny we can now make our batteries that can actually cause electrical charge to go through a loop. Does that make sense what I'm getting at here? Like, this is, to me, I started the class with this. This has got to be like a top 5, top 10 scientific discovery of all time. Like, this has fundamentally changed our lives, right? I mean, electricity allowed us to do a lot of cool things. Batteries allow us to do cool things wherever we want, right? I want to go camping. I don't actually have to use fire in order to light up things at night. I can have a flashlight. That's incredible, right? Oh, anyways, I'm getting off topic here. Hopefully I'm doing a good job, though. Where did I finish here? Okay, Leo says Gur. Well, once they discovered that really oxidation and reduction involved transfer of electrons, we've now changed our definitions. Okay, reducing things is still involving taking compounds and turning them into pure metals. But really, the better way of looking at it is reducing things means someone is going to gain electrons. Right, let me show you one more. I'll do aluminum. Here's that bauxite I showed you earlier. Here's bauxite. I'm going to take it and turn it into aluminum and oxygen, and to balance it, it's going to have to look like this. No, that's a 4. This is bauxite being reduced from an ore into a metal. Yes, that part is true, but so is the electron part. What's the charge of this regular old aluminum sitting here? 0. What's the charge of any metal cation going to be? Well, either +1 or +2 or probably +3, one of those ones. It could be +4 or 5, but chances are it's a positive. In this case, it's +3. Doesn't this make sense that in every single case, you're going to go from a positive number to 0? Isn't that going to be involving the gain of electrons, in this case 3 electrons? If we can find a way, when this reaction takes place, to have those electrons run through a loop, now we've got a battery. It's brilliant. The same thing happens over here in oxidation then. only it's the reverse process. So let me draw out a basic oxidation reaction. Let's take some copper, and let's have copper be in the presence of oxygen and have it turn into copper oxide, something like that. We would call this oxidation historically. Two reasons why. One, we call it oxidation because literally it reacted with oxygen. Okay, now we actually know that's actually kind of a poor definition. It doesn't have to be oxygen, but the better reason why is a metal turned into a compound. Something pure became impure. Right? Normally we don't want this, right? The rustiness that's on our cars, our tools, it usually flakes away. It ruins its integrity, its structural integrity. So we normally don't want this. But let's look at the charges here. What would the charge have been on copper as a pure metal? 0. Why 0? It's an atom. What's the charge on an atom? Well, neutral. In this example right here, I picked copper plus 1 in this example here. Well, how does something go from a 0 to a plus 1? Two possibilities. To go from a 0 to plus 1, you either become more positive. Can you become more positive, though, in chemistry? Can you add more protons? If you add another proton to carbon, I can't tell because Nick Foles is over top of every single one of those. Whatever. Copper, zinc, maybe? I don't know. Whatever is after copper, if you could add another proton, you would literally change what it is. So we know we can't add protons. But what we can do is we can remove electrons, right? So to go from 0 to plus 1, you could have lost 1 electron. So our modern day definitions of oxidation and reduction now have more to do now with, does something either gain or lose electrons? Which takes me back to where I started class with me giving Daniel money. Someone is going to take money and someone is going to give money. In the exact same examples in chemistry, when we're talking about electrons, someone is going to be the electron giver and someone then has to be the electron taker. Does that make sense? We now give those things different names. Electron givers, for lack of a better way of describing it, would be your anode. And the things that take electrons would be your cathodes. We're going to get to that a little bit later in the course, but that's the terminology bit. Anybody have any questions so far? Okay. This is another acronym that you can use, or mnemonic, to memorize things. It's oil rig. I never learned this one. I always say Leo says Gert, because that's what I learned. It's silly, but it works. But you could say that oxidation is losing electrons and reduction is gaining electrons. But you need some way, though, of knowing which one is which. So here's some slides then that kind of talk about what I've been saying as we go along. What then is an oxidizing agent? The oxidizing agent is somebody who promotes somebody else to oxidize. Okay, let's write a quick reaction here. Let's do, well, we need an oxidizing reaction. Let's do iron plus oxygen to make iron oxide. There's a really basic example. How do I know this is oxidation? Well, first of all, I'm adding oxygen to it. How else do I know it's oxidation? Well, it's going from a metal to a compound. That also works. How else do I know it's oxidation? Let's look at its charges. What's the charge on this guy here? 0. What would the charge on this guy right here be in the compound I chose? Iron's either, what, 2 or 3, right? But you guys know the charge of oxygen? -2? You guys know this, right? Okay. So then if this is -2, this guy's +2. How do you go from a 0 to a +2? Well, either you gain protons, but I'm going to stop saying this because this is getting redundant. You either gain protons or you lose 2 electrons. So now I have 3 ways in which I know this is oxidation. Method 1, literally you added oxygen to it. That's why we call it oxidation. Or 2, I went from an element to an ore. That's another reason why. Or a more chemistry-based definition. Now that we know about subatomic particles, we went from having no excess charge to having a +2 charge. That meant you must have lost electrons. Okay, so let's talk about the oxidizing agent. Who's the oxidizing agent? Oxygen. Good job. Because oxygen promoted iron to become oxidized. In terms of vocabulary, which is basically my only goal today, you would say iron got oxidized and this oxygen was the oxidizing agent. I want to point out one more thing, though. You know how we talked about redox reactions, where there's reduction and oxidation? Hang on. If iron lost 2 electrons, somebody else has to gain 2 electrons. Let me show you where that is in a new color. I've already drawn out the fact that right here oxygen is -2. Because we know oxygen is charged and a compound's -2, right? It's in group 16, everything in 16 is -2. What would the charge on this oxygen right here be, though? 0. Why? This oxygen is it's an atomic form, isn't it? I know there's 2 of them still, but isn't this oxygen right here in its atom form as opposed to an ion form? So really, this guy has a charge of 0 as well. Well, now let's consider how oxygen changed. Oxygen went from 0 to -2. How do you go from 0 to -2? By gaining, wait for it, 2 electrons. Hang on, you lost 2 electrons? You gained 2 electrons. Doesn't it come full circle? I gave Daniel $10. He took $10. That's the only logical way it would work. So here's what this means then. This was actually a redox reaction because there's actually both reduction and oxidation happening at once. I'll use colors again. The reduction, Leo says Gur. I'll even write it out here. Leo says Gur. Who lost electrons? This guy down here did. So in red, iron was oxidized. But who was reduced? Oxygen was reduced. Does that make sense? Because, according to Leo saying Gur, gain of electrons is reduction. See how oxygen gained electrons? If someone's going to lose electrons, somebody else has to pick them up, right? Law of conservation of charge. You can't just all of a sudden have random electrons being lost. So that's why we now call this, I think I've now come full circle, that's now why we call this redox. Because there was both a reduction and an oxidation taking place simultaneously. Again, if we can find a way mechanically to separate the electrons out and make them go through a circuit, now you've got yourself a battery. But we're a ways off. We're not ready for that yet. Any questions? Okay, let me go through whatever slides I have here, see what else is relevant. What's the reducing agent then? Well, the reducing agent is somebody who causes reduction in something else. All right. So why don't we just, for the sake of argument, let's do one more here. Let's have, I'm going to steal the reaction from before, though. What was one here? SnO2 plus, well, I'll just use it here. Let's just talk it through. Who's being reduced in this equation here? Just look at it. Don't bother flipping. Who is being reduced? Tin. Does that make sense? I know this for a couple of reasons. One, tin is going from a compound to a metal. Hence the name reduction, because we were literally reducing its size. It used to be a big compound. Now it's a pure metal. I also know it's being reduced because this went from having a +4 charge to having a 0 charge. In order to go from +4 to 0, you must have gained electrons. And Leo says Gur, gaining electrons means that this guy was reduced. So who's the reducing agent? Copper, or carbon. Carbon is the reducing agent. Is that clear? All right, let's go find my examples at the end, because I think that's where we need to go here. Yeah, here we go. Let's try this one here. So now that I've given you all the terminology, all the vocabulary we need, let's just try a basic reaction now and see whether you guys can label everything. I'll get you started, and then I want you to try it yourselves, because I've done too much of this. We are going to take a piece of zinc metal and place it in copper 2 sulfate. So right off the bat, don't be afraid to use all the previous skills we've learned. I mean, okay, so zinc metal is Zn solid, and we're going to add it to copper 2 sulfate. So that's CuSO4. It said it was a solution, so that kind of gives a hint as to what state of matter it should be. It should be aqueous. Okay, I know this is going to be redox, because clearly it's going to be, this is the unit we're talking about, but what other category would we call this kind of reaction? From like, if you're in grade 10, you'd call this, okay, so do single replacement. So that means you're going to need copper solid by itself, and zinc sulfate, probably in an aqueous format. Okay, so here's my challenge for you guys. I'd like for you to tell me 4 things. Tell me who is being oxidized, who is being reduced, who the oxidizing agent is, and who the reducing agent is. Does that make sense? Who is being oxidized, who is being reduced, who's the oxidizing agent, who's the reducing agent. Give it a try. While you're writing this, I've definitely seen diploma questions which are numerical responsed, where it's more of a matching. They'll give you some equations, and then they'll say which one of the following is the reducing agent or is the oxidizing agent, and they make it numeric response as like okay, well this one goes here and this one goes here. Does that kind of make sense how you could design a question out of that? Where they're just testing your terminology. There's no work to this. You literally should now be able to look at it and just tell me. Right? And so hopefully over time you're getting better at it. So. Hey Google, what's a reducing agent? This is fun.
Reducing agent, a substance that tends to bring about reduction by being oxidized and losing electrons.
Okay, that was a little complicated. I think the first part it said, though, is a reducing agent is someone who brings about reduction, right? So I guess in order to do the bottom two, it may be best to do the top ones first. Let's figure out who gets reduced. You can do this through one of 2 methods, probably. The first method would be you try to figure out who is going from element to compound or who's going from compound to element, or you can also do it using charges. So I'll do both. Zinc's charge here is 0. Copper's charge here must be +2. Now copper's charge is 0, and zinc's charge is +2. Am I okay just blitzing through that? I don't need to go over that again. Basic grade 10. Awesome. Okay. So as I look at it, zinc went from 0 to +2. I often draw arrows to help me internalize this. So feel free to do the same thing. To go from 0 to +2, you must have lost 2 electrons. And conversely, to go from +2 to 0, you must have gained 2 electrons. First of all, if it's not the same number, you screwed up, right? Because it can't be 1 gaining 2 and 1 losing 5. Right? There's no way that works. Well, if you know your Leo says GER, your silly little acronym there, loss of electrons must be oxidized. And gain of electrons must be reduction. So let's see, who got reduced? Just copper. I want to point that out. It's just the copper that was reduced. Did the sulfate get reduced? We actually had a name for this from a previous unit. What's the sulfate called? I heard it. Yeah, good job. Well done. Yeah, it's spectator ion, right? Well done. Props. Yeah, so the sulfate actually is not being reduced at all. The sulfate's just kind of tagging along for the ride. Right? Now, the thing that was oxidized then is your zinc. Now, here's where I want to make it clear, though. Your reducing agent is the thing that causes something else to become reduced. So if we agree that this thing right here was reduced, it's this zinc solid right here that caused copper to be reduced. However, zinc is what was oxidized, right? What was the agent that caused it to be reduced? In this case here, though, I would call it the copper sulfate, because this entire thing caused that guy to change. Okay? When we talk about an oxidizing or a reducing agent, we talk about the entire compound, including the spectator ion that might be attached to it. When we talk about who is oxidized or reduced, though, we just talk about a specific element. Can I say that one more time here? This zinc is what was reduced, and this zinc is what was oxidized, and this copper is what was reduced. Okay, as atoms. They were reduced or oxidized from atoms to ions. The SO4 did nothing. Okay, but when we talk about the agents, agents are the entire compounds. So these guys right here will always just be just one item, just one element. These guys right here will be like the entire compound you have there. So it may mean that when I talk about an oxidizing agent, I'm actually talking about like an entire thing. And it could be a complicated compound, like say something like this. That could be an oxidizing agent. And there's actually three things as part of it. Does that make sense? Okay. This is an activity that I'm going to do more tomorrow, where we're going to talk about another concept called spontaneity. But I've got a picture on here that hopefully works. Here's a basic reaction here. I'm going to take copper. I'm going to add it to silver nitrate. I don't know why there's an R in the middle there. That should be like an arrow. So ignore that R in the circle. Make that an arrow. We're going to take copper and silver nitrate, turn it into copper nitrate and silver. If I were to ask you to classify this reaction, in grade 10, you would have called it single replacement. In grade 12, I want you to call it single replacement and redox. And again, we know this because I'm just going to use the numbers this time. Copper is going to go from 0 here up to +2. And here silver is going to be 0, and here it was +1. Clearly, numbers are changing, right? Atoms are turning into ions, and ions are turning into atoms. There is definitely electron transfer taking place. What we sometimes do then is, although this entire reaction is called redox, sometimes we write something called a half reaction, which is literally the two halves of our entire piece. Here's the two half reactions. One of them is how silver turned into silver solid. See how right here? This silver turned into that silver solid. Do we actually care about nitrate? I mean, we love nitrate a lot, but in this case, did it have to be a nitrate? No, it was a spectator ion. So we don't actually need to write the nitrate in our half reactions. And then the same thing happens here. Here our copper turned into a copper ion. It went from copper normal to copper +2, hence I'm writing the +2 right there. Now here's what's unique about half reactions. When we write half reactions, we include electrons as part of the reaction. Let's say that one more time. When you write a quote-unquote half reaction, we include electrons as part of it. So see how right here, this silver right here turned into silver solid? Well, I know that for silver to go from +1 to 0, it had to gain 1 electron. Well, literally, that's what I'm showing right here. Here is the silver gaining an electron. You know how in our first unit we talked about writing an energy either in the reaction or out of the reaction, either as a product or reactant? Well, I'm doing the same thing here now with electrons. Well, the same thing here happens in copper. Copper went from 0 to +2. It must have lost 2 electrons. Well, here's the copper going to the copper +2, and here it is on the product as though it has now lost 2 electrons. But did it really lose those electrons? We should maybe flip the order. It might have been better to start with this one, because this guy lost 2 electrons. Where did they go? Well, this guy picked them up. Oh, wait. This guy lost 2. This guy picked up 1. Doesn't that break the rule we just talked about? But why is it not right? Why is it still okay? It's not balanced. Yeah. This reaction up here, the one I first started with here, I never actually balanced it. So I know there's a mess of jumble up there, but can we balance it real quick with a new color here? There's 2 nitrates over here to 1 nitrate over here. You better put a 2 there. You better put a 2 there. Well, hang on. How does that affect our half reactions down here? Well, now we had 2 of these going to 2 of these. Wouldn't it make sense that you'd need to have 2 electrons? It actually does come full circle, right? If it's not balanced properly, your electrons won't be equal, because you have to have equal gaining and losing, right? So, in terms of terminology now, I think I've taught you 6 main things. You should now know what is reduction, what is oxidation, and you should be able to do that in a couple of ways of doing that. You should also be able to tell me what an oxidizing agent is and what a reducing agent is. And now finally, you should be able to write for me a oxidizing and a reducing half reaction. where all you're literally doing is writing out half of the reaction, and it always involves electrons on either the product or reactant side. So, I had one more example here, don't I? Let's go to the last one. We'll call it a day. So I've shown you a lot of stuff today, most of it vocabulary. Here's your task. I want you guys to predict the products, give me half reactions, and label oxidizing and reducing agents when you take zinc and add it to lead nitrate. And go. See what you can do. Again, while you guys are writing, there's no work to this in a way. Like there is a little bit at first, but as you guys get better at this, if you guys can imagine, this is like entry level stuff. This is basically just recognizing what to call things. So these are going to be very, very basic recognition type of questions you're going to get. There's no math to this part. Hey Google, play some fun music.
Oh. Sure. Here's a Google Play music station called Sunshine in Me.
There you go. Now you got some fun music to play too. Hey Google, you can stop now. Hey Google, stop. There you go. Okay, so maybe I want us to play fun music. This could be good though, hey? My little assistant there. Hey Google, play the Jeopardy theme song.
Since I couldn't find the song Jeopardy theme song in your music library, here's a similar mix on Google Play Music.
Hey Google, stop. Alright, so here should be your first step. If I haven't distracted you too much, you should have a chemical equation written out because ignore the fact that it's redox. Just write out a normal chemical equation of single replacement. So lead nitrate plus zinc goes to lead by itself and zinc nitrate. What's our spectator ion? Nitrate. We don't really care about nitrate all that much. It's actually balanced already too, isn't it? Okay, so let's start writing out some of the things we want. We want to figure out who is being oxidized and who's being reduced, and we're going to write out an equation. Eventually, you get a lot faster at this. I right here have a lead 2+ ion right here, which is going to turn into a lead solid. I also have a zinc solid, which is going to need to turn into a zinc 2+ ion. Because I can see there's a +2 here, there's a +2 here. That guy's a 0, and that guy's a 0. Well, once I start writing out the basic framework, now I just got to figure out which side do the electrons need to go on. So if I go from 2+ down to 0, which side do I need electrons on? The products or the reactants? Yeah, we need 2 electrons right here, because 2 positive and 2 negative make it neutral. Well, then it's the opposite here. Here, neutral is going to go to 2 positive and 2 negative. There, I've got my half reactions written out. Which one is which? Leo says Ger. Who was gaining electrons, A or B? Lead or zinc? Well, lead is gaining electrons, right? So according to Ger, that makes that reduction. who is losing electrons. Is it clear here that the guy that's losing electrons must be the second reaction because the electrons are a product? So that must be your oxidation. Last bit here, we need the oxidizing and reducing agents. Okay, so the oxidizing agent is the person that causes somebody else to get oxidized. So zinc was oxidized. Zinc is oxidized. So this whole thing was my oxidizing agent. And the reducing agent is the thing that makes something else get reduced. Lead is what got reduced. So this lead right here, what caused it to get reduced? This guy here is my reducing agent. And all the identification we need. Does that make sense? Okay, so quick summary. I think that's my last slide, right? Yeah, okay, so quick summary. We learned a lot of vocabulary today. We learned a little bit of history, even. We talked about Donald Trump. Yeah, we had a good lesson today. We talked to Google a little bit. Here's some of the basics you need to know. Okay. You should know oxidizing agent, reducing agent, oxidize, reduce, redox, half equations, half reactions. You should hopefully know the acronym Leo says GER, because that's quite useful. But pretty much above all else, all I need you to do right now is when I talk about a reducing agent, you should know what I'm saying. When I talk about oxidation, you should know what I'm saying, okay? Because we're really not doing anything with this yet. But I have definitely, guys, I have definitely talked about where this will be useful. Have I done a good job of explaining the idea that if electrons are going to be transferred, if I can find a way to transfer them the long way around a wire, I can make a circuit. And that's brilliant. Right? So we're going to get there, but we have to build our way to that stage. But that is ultimately the goal of this unit, is to talk more or less about how we can create batteries. Sound good? Okay. You guys have a few minutes left here today. Finish your unit test if you haven't, I guess. Maybe print off some notes and assignments for tomorrow. Sound good? Sure. Sounds good. Okay.